are placed on your subgroup H, and here are those conditions, right? Particularly this this one. So after a while, the subgroup H that satisfies these conditions will get a special name. I won't introduce it yet, because we're not there yet, but we will give a special title, label, to a subgroup that has this property. But that's for later. All right. Okay, now it's an if and only if statement, so as usual we have to prove it both ways, and convention is start with the if. So call this statement P, call this statement Q. So P if Q, P is true if Q is true, so start with Q and derive P. So so the if is from Q to P, from the right hand side, prove the left hand side. Right? So we start with Q. So given this, right, and we have to prove this. We have to prove that. Now to prove this, the left hand side, to prove this, what's going on here? This is a coset times the coset. That still gives you. This is also a coset. So we've got here the equality between two cosets, which is the same thing as the equality between two sets. Right? And to prove the equality between two sets, you have to prove two things in effect. You have to show that two sets are equal. You've done this many times now. You have to show one is a subset of the other, and the other is a subset of the one. So a two-part proof. All right. Okay. So. Yeah, so we have to show the one is a subset of the other, and the other is a subset of the one. All right? Okay, so let's prove this one. Now, how do you show anything as a subset? Well, I've done this also many times. To show that this is a subset of that, we have to show that if X, well G if you like, any member of your group, big G. So if any member is a member of this, therefore it's a member of that. If that's true, for all G, then this is a subset of that by definition. That's how you define a subset, right? Okay, so let's take any element of big G and let it belong to this, and then we will prove that this G, little g here, also belongs to that. Okay? And if so, that is a subset of that. Right? So let's try to prove that. Alright, so G, we start with G belongs to this, the left hand, this part. G belongs to that. Now if that's true, G must be equal, it must be of this form. Right? There'll be some member of H, call it H1, and there will be some member H2 of H, so that G is of this form. Right? If G belongs to this, it must have that kind of, it must have that form. So H1 and H2 are just members of your subgroup H. Right? Now here's a bit of a trick, and we'll see why in a minute. So here's your G, AH1, BH2. Right? Now that's the same. Just put an E in the middle here between A and H1. And why do you do that? Well, you'll see. It's just a trick, but it helps the proof. Right? Now E you can rewrite as B inverse. Okay. So this E now becomes B inverse. Now here you've got B inverse H1B in the middle here. A, B, and these three, H2. Now look, now where'd this come from? We're doing the if statement, right? So we assume this. We're given that, we have to prove it from right to left. Now, we know that's true, right? Because we're given that. We're given Q. We have to prove P. So we assume Q is true. So, and that's true for any X any element of your big G. All right. So if that's true in general for any x, then if x is b, then you have any element h here. So b inverse h1b is some h here. So that must be true for some h belonging to your subgroup. That must be true, right? For some h. All right. So these middle three, b inverse h1b, you can just replace with h. Now the reason for doing that trick, this e thing, was so you get this, and by having those three, you can use this. Right? That's the trick. That was the reason. All right. So we can rewrite G now as a b h h2. There it is. A b h h2. Now G's are subgroups, so it's still a group, and therefore this product HH2 must belong to H, right? H is a subgroup, it's closed, so HH2 must belong to H, and so we can call this just H3. So G is of the form AB H3, okay? Where H3 is just one of the members of your subgroup. All right. So if G is of this form ABH3, then G must belong to ABH. Right? If G has that form, must be a member of this. All right. Now I've wiggled the line underneath. If G belongs to this set, then we've proved that G belongs to AB of H. So if it belongs to this set, therefore it belongs to that set. Therefore this set is a subset of that set. Right? Therefore this is a subset of that. I've written down here. Right? So only part way. Alright, now let's go the other way. Now let's try to prove this. So we now need to try to prove that this is a subset of that. So now, okay. So let little g, that's just any member of big G, of your original group. So let G belong to this. And then we'll try to show that G belongs to that. If G belongs to this, then G belongs to that. If that's true, then this is a subset of that. Definition of a subset. Right? So let little g belong to this here. Okay. Now if that's true, G must be of this form, AB times some H1, which is a member of the subgroup, right? Okay, now, so I just post-multiply it by E, again a trick. So I can rewrite G as ABH1 becomes ABH1E, no change, the value is the same. Now for E here, I can replace that with B inverse B. Right? That's just E. Now why do I do that? Well, because then I've got this form B H1 B inverse, and that means I can use this again, right? Because we're starting with Q, we're trying to prove P. So you do this trick so that you can actually use Q, bring Q into your analysis, right? Now this is true. That's true. That this is a subset of H for any member of your group, any X of your group. Okay. So for any X, so if X is equal to B inverse, then if X is B inverse, then X inverse is the inverse of B, such as B, H1, X, well X is B inverse. So you get this, B, H1, B inverse is H, right? But, because this is a subset of that, right? So this must be equal to H for some H in this subgroup. Alright? Okay, so now rewrite G, and where are we? We're here. So just for these three here, just put H, right, here. So you'll get AHB. There it is, AHB. Now that's the same thing as AHBE, right? E the unit. No? And why do you do that? Well, because if G is of that form, AHBE, then G must belong to this set, right? Because it's of the appropriate form. See, E belongs to H, little h belongs to H, so G belongs to this product, right? Alright, so I've put the wiggle here and here. So if G belongs to ABH, then G belongs to AHBH. Right? That's the definition of a subgroup, subset. So therefore, ABH is a subset of AHBH. ABH is a subset of AHBH. Now put rectangles around these two. Here you've got AHBH as a subset of ABH, and here you've got ABH as a subset of AHBH. Put the two together, and the only way the two are compatible is if they're equal. So therefore, AHBH equals ABH. Right? So we have now proven this. So we're only halfway there, right? It's an if and only if. So we've proven from Q to P. So if that's true, then that's true. And that's what we've got down here. Alright, now the only if P is true, only if Q. So the only way you can get P is Q being true. So if you do have P, you must have Q. So if P, then Q. So the only if P then Q. So we're going from the left-hand side to the right-hand side. We start with this and we have to prove that. Start with P, have to prove Q. Right? So we start with P, which is this. Right? We're given that now. Right? Let's see. And that's true for any elements A and B of your group G, right? Okay. Now let X be any member of your group G. Right? Now let